Continuing with Chapter 4 on vectors, we are now at the part where we have gotten to unit vectors, the concept of unit vectors. Now, before I even start describing this, I need to tell you that this is nothing you have not had already. It's just another way of notating it. What unit vectors are is describing a vector by its x component and its y component. Let's say, for example, you went, I don't know, you're going this direction right here. All right, whatever that direction is can be described in two ways. That is, you traveling some distance in the x direction and traveling some distance in the y direction. And those directions are like our axes, okay, the x-axis and the y-axis. And in fact, to indicate the x-axis and the y-axis, we use these things. I'm not even sure exactly what they're called, but we call them just hats. It looks like a little hat. That little accent mark right there indicates that we're talking about the x direction right there, or the y direction right there. So wherever you see some value with an x hat after it, you're saying it's okay. It's that value on the x-axis only. Okay, so this vector right here that is being drawn right there, it's some value x hat plus, or we add the y component of that, plus some value y hat right here. That's how we notate that. It simply means, it's just like when we did unit vector component problems, but we're just kind of describing a vector as being composed of those two parts. All right. So, any vector, vector A, for example, instead of saying vector A is so-and-so paces at something degrees above the something axis, we can describe it this way as well. We can say, all right, A is simply composed up of A's x component, whatever that is, and in fact, it's AX right here and it's AY. I'm going to just give those numbers, for example. Let's say vector A is 5. That's the x-axis is 4 and the y-axis is 3 right there. Okay, so that means vector A right there could be described as 4 paces or 4 meters or 4 whatever you're measuring, 4 x hat plus 3. Oh, it's a terrible 3 y hat. All right, so it's basically saying it has an x component and a y component. All right, so when we add vectors together, saying that, let's see, vector C equals A plus B. Okay, we've done that before. This is how we would notate it. So we would say that vector C is made up of the A x component and the B x component, and then that's told to us by this x hat after it. But this is not multiplying anything. This is just simply saying all the stuff is in the x direction, and then plus the y component of A plus the y component of B. By the way, this means all that is in the y direction. Again, so these funny little x's with the hats over them and the y's with the hats over them, they're nothing's being multiplied here. They're just, you can think of it as just being a notation. All right? Well, this last one right here, vector D, it's like saying, okay, vector D equals vector A minus vector B right here. We're subtracting the x component of B and we're subtracting the y component of B right here. But the way we can do that is just like setting up a chart where we would add or subtract all the x's together and add or subtract all the y's together and have a final x and a final y. That's what this notation means right here. It's basically telling you about a vector based on its two parts. Okay? That's what this means. So, and some of you have come across this already. If you're looking for a triangle right here, oops, I'm going to do that. If you're looking for a triangle right here, you've noticed that you can take, maybe you have a vector x and a vector y right here, and the resultant is vector a. Okay, I'm sorry, I should say component x, component y, and the resultant is the full vector a right here. Some of you noticed that well, this is the same thing as this right here, so you just moved it over there and made it into a right triangle. That is absolutely true. You can do that. But this is basically saying that each vector is made up of two parts to it, and the y component. All right, now we're going to do a couple of examples of that a little bit later on, but as we move forward, I want to give you some kind of examples of different kinds of vectors. Now, we've been talking mostly about displacement vectors. For example, if you start right here and you're displaced 5 meters east, and then you're displaced 4 meters due north, or something like that, what's your total displacement? That would be indicated by that full magnitude vector right there. But there's other kinds of vectors that I'm going to be telling you a little bit about. So a position vector. A position vector is simply a location. It's saying that this is a point right there. And that point, or where you are, is indicated by some distance x and some distance y from the origin. That's how we notate that point, or that position point right there. Some distance x and some distance y. All right, well, here's another point right there that you've moved to. Okay, so here's your initial position, here's your final position, and then, as you probably guessed, this right here, or your change in r, is going to indicate, well, how you changed your position between your initial and your final right here. All right, so we would subtract this position vector from this position vector, and that would tell us, or that would describe to us, how this displacement vector changes. All right, it'll make more sense when we actually go through it, but I hope that makes some sense to you right now. Do we have? We have velocity vectors. All right, remember, velocity is, you might say, speed in a given direction. Okay, and a velocity, as we know before, oops, I'm trying to draw here. Velocity is described as a change in position over a change in time. All right. Well, if on a previous slide we indicated a change in position as delta r, we're just going to go with that. Okay. But you'll notice that it is over a change in time right here. That's our average velocity vector. Okay. So it's got to be in the same direction as the change in position. All right, because you can't have a velocity north and be displaced, and have it displace you south. All right, the velocity has to be in the same direction as you are actually being displaced. Okay. See, what other kinds of vectors do we have right here? What other kind of unit vectors do we have? Well, we have acceleration, which we'll get to a little bit later, but let's do an example first. Okay. Example 4-7. All right. So this is saying that it has an initial position. The initial location of it is 2 meters x hat and 3 meters y hat. Okay? And then the final position is negative 3 meters x hat and 5 meters y hat. I probably should have done that in a different color right there, but that's all right. Okay? So we want to find out what the displacement and average velocity are during this time. Okay, remember the displacement. We're going to call delta r. All right? And so that is our r final minus our r initial right here. Okay, so how do we subtract vectors using unit method? Unit vectors. Sorry. We do it this way. So r final is negative 3 meters x hat Oops, I should have done this right here. All right. X hat. You're thinking, why did he make those parentheses so big? Well, I'll tell you in just a minute. And our final is 5 point. That should be a 5 right there. I'm getting kind of sloppy. 5.5 meters. Y hat. All right. Now again, why did I make those parentheses so big? Well, again, if we're subtracting this vector from that, then that means we subtract all the x's from this to that, and then we subtract all the y's. So we can really describe subtracting these vectors, vectors in unit vector notation, as being we're taking negative 3 meters minus the r initial x hat, 2 meters. Okay, so this is the r final x hat, and this is the r initial x hat, and we're subtracting it. We're also subtracting the y hat component, of vector r initial. So minus. So as for the y, it's this y hat minus this one right here. So minus 3.50 meters. And that's all in the y direction. So it's kind of like we're setting up a chart or a table, but we're just sort of doing our subtracting within parentheses right here. Okay, so delta r, our resultant vector of the r final minus r initial position vectors right here. What does this come down to? Well, minus 3 minus 2, that gives us a total of negative 5 meters x hat, okay, plus, now it's always going to be plus right here. Even if the two things are being subtracted, you always have your x component plus the y component right here. So in between the x hat and the y hat, it's always going to be a plus. Plus, what's this? 5.5 minus 3.5? 5.5 minus 3.5? That should be easy. It should be 2.0 meters. And that is in the y hat direction. All right? And that is our value of our of our displacement vector. All right, from the initial position to the final position has just been displaced in the negative x direction 5 meters, and it's been displaced in the positive y direction 2 meters. Okay, so that's our displacement right there. It's also asking us for the average velocity as well. I'm going to do this part in blue right here. Koa, quiet please. My dog is yipping in the background. Remember, velocity equals our change in in displacement over our change in time. All right. Now, the easy thing about this is, and I'm going to try to move to a different room so she doesn't bother any of you guys. The easy thing about this is that we've done pretty much the hard part already, because we already have a displacement vector in unit vector notation. All right. So all we have to do is divide that by the amount of time that is being elapsed. I'll show you what I mean. All right, so that equals what? Negative 5 meters x hat, and you can think of that as an and rather than a plus, but and 2.0 meters in the y hat direction. Okay, so that's the displacement. But each of these displacements has taken place over a certain amount of time. All right, what time is that? That's 3 seconds. That's 3 seconds, and that's 3 seconds. So all we need to do is divide out our 5 divided by 3 and our 2 divided by 3, and that'll give us our velocity in the x and in the y direction right here. All right, so 5 divided by 3, what's that? 1.67. Oh my goodness! I'm sure you guys are loving this. Her barking in the background. negative 5 divided by 3. All right, so our average velocity is going to be 1.67. Oops, negative, right? Negative 1.67. What units is that? Well, it's meters per second, right? Meters over second. And again, this is the velocity, so that should make sense. Meters per second x hat. And 2 divided by 3. What's that? That's 0.67 what? Meters per second in the y hat direction. And that, my friends, is our average velocity in unit vector notation. One more step, but really isn't that hard because we're simply dividing our unit vector displacement by time to be given a new value for our unit vector, our velocity unit vectors in the x and y direction. So that's example 4.7. I'm going to give it a break right now and come back and do example 4.8 and the rest of the notes in the next video. See you then.